as I said at the beginning, the Aquarius has two different pressure vessels. These can be equipped to take two size battery modules. So the battery modules are 6 lithium-ion battery packs in two different sizes to go with the two different size pressure vessels. So as you can see in the diagram in the middle, we can take 2 of these battery packs out, or 4 of them out, to create different terms for the battery deployment. Now, this is useful if we have specific financial constraints or if we're only planning on deploying for a specific amount of time. So we could take all battery packs out, which would provide us with no power at all. If we only included 2, then we'd have a short-term deployment. If we included 4, we'd have a medium term. And if we include all of them, then we have the long term. And any packs that we remove, we will just replace with dummy weights so that we have the same buoyancy, whatever configuration we have. As ever, the maximum deployment time is dependent on the sensor configuration and the communication. So if we are using all of the seismic sensor, the hydrophone and the APG, and communicating data all the time, then naturally we will use up our power more quickly. The Aquarius is equipped for super fast recharging, roughly 1 hour per month of deployment. So for example, if we are out on a recovery mission, we could recover an instrument, plug it in to recover all of the data. Simultaneously, we could be recharging the instrument. We could proceed to go and recover another instrument. And by the time we have recovered maybe 1 or 2 others, we could then have the first one ready for redeployment. This means that we don't have to return to land and therefore minimizes our ship time. On a practical note, we have confirmed that the Aquarius can be shipped via sea and air freight. We have shipped the Aquarius to AGU last year. We have shipped it to a number of customers via air freight, and we now have all the documentation in place to ship via air. It can also go via sea. So any practical considerations regarding the dangerous goods element of the lithium batteries, we are now fully equipped to deal with. So carrying on with battery life, as I said, the various configurations will have an effect on the battery life itself. So if we look on the left-hand table, a standard configuration might be expected to include just the hydrophone with no communications activity going on. The hydrophone is fairly standard because we use this to listen for any noise in the water column that will be affecting the seismic sensor. And we can therefore use whatever the hydrophone is picking up to eliminate the noise from the seismic record. If we're into the maximum specification here using the APG and using all of the features available, then we might be coming down to around about 12 months. If we look on the right-hand side, the Aquarius Plus with the larger battery packs, here we have roughly the same amount of time as on the left-hand side. However, we are also transmitting data to the surface. So if we didn't transmit data, then we would have the maximum battery life, if you can see right down at the bottom, is around about 21 to 24 months. So that's using no communications, but we are still using the hydrophone to eliminate that water noise. Okay, moving on to installation and recovery. As I said, the Aquarius is USBL and GPSA compatible, so we have a very good idea of where it is on the seafloor. We can use the acoustic localization tool in Discovery. This makes use of the acoustic modem, and we can effectively triangulate the position of the Aquarius on the seafloor. And to top all of that, we can communicate with it during installation. This means that we can wait for it to hit the bottom. We can then communicate to get some noise plots, decide whether our sensor is deployed effectively or not. And if we are not satisfied, we can retrieve it back to the surface, fit some new ballasts, and then redeploy somewhere else. This is a key feature that most OBS units do not have. Most free-fall OBSs we would leave over the side of the ship and then hope that they land in a suitable condition for when we recover them a few months later. In addition, for recovery, we have the standard LED identification light and a satellite tracking system. Again, as I've just mentioned, we have the super fast recharging for redeployment, even while we're on the same ship. And we have the replaceable steel ballast, which is released upon acoustic command, upon a timer, or upon a critical battery life, all of which are operator configurable. So we can configure the timer and also can configure the critical battery life level at which the battery will release the ballast. This means we have a series of redundant mechanisms so that we will always get the OBS back to the surface. Okay, moving on to some applications. We'd like to thank the Dublin Institute for Advanced Studies, or DIAS, for allowing us to feature the Aquarius on our webpage. DIAS have installed an Aquarius 200 kilometers off the west coast of Ireland in the North Atlantic Ocean. So this Aquarius is communicating seismic data to a weather buoy that was already existing in the ocean. This weather buoy is an existing piece of infrastructure. So we just attached our seismic modem onto the side of this buoy, and it transmits data back to the mainland. In this case, 200 kilometers was obviously not a viable situation to be cabling offshore. So instead, we make use of existing infrastructure that is there. So here you can see a map of where we are. Here you have the weather buoy on the left-hand side, and the red triangle marks the position of the Aquarius. We're just off the west coast of Ireland, just on the continental rise. So future deployments and applications. 2 Aquarius units are currently in transit to be deployed in the Pacific. We have a lot of further interest coming from institutions monitoring subduction zones, offshore gas reservoirs, as well as national and international pools. There's especially a lot of interest in using these instruments for forming rapid response campaigns. The idea of a rapid response campaign is that you have minimal effort to go and deploy the instrument, but then instead of waiting for months to come and collect the data, we want to be able to communicate and retrieve data in near real time. So for example, if there was a large earthquake in a subduction zone, we want to go and monitor any aftershocks or swarms that are occurring just after the main shock. This would require a small vessel perhaps, going out with an Aquarius, dropping it over the side of the ship, and then regularly going out with the modem in a much smaller vessel to go and retrieve seismic data on a regular basis. Not waiting for the OBS to come back to the surface in a few months' time. So in addition to this, we do have the standard areas of seismic research, energy exploration and noise surveys, aftershock monitoring, and earthquake and tsunami warning and forecasting. Thank you for coming to the presentation today. My name is Will Rice. I'm the Global Sales Manager here at GrowUp. Please feel free to email me or call me up on my cell. And once again, thank you very much. If you did come to AGU, then I hope you have a very good conference.